Hey guys, welcome back to hypothesis testing with t-tests. Remember that last video, the single sample t-test, and how easy that was, right? All you had to calculate was the sample mean, the sample standard deviation, remember the n-1 part, and then get standard error from that by dividing by the square root of the sample size, and otherwise it was just like a z-test, right? It was extremely easy, really straightforward. The 6 steps of hypothesis testing, although maybe a little clunky, helps guide you right through the whole thing. Well, this next lecture is about paired dependent samples t-tests. And to preview, it's damn easy, almost identical to the single sample t-test. In fact, after one step, it does become identical, if maybe even easier than the single sample t-test. So let's get started. First, let me tell you a little bit about a really amazing statistician, this woman named Stella Cunliffe. Stella Cunliffe was hired by Arthur Guinness and Son Company to be a statistician, and in fact was head of their Department of Statistics at one time. And one of the things that she was in charge of was quality control. And so back when barrels were made by hand, they had to be made by these coopers, right? And they had to take all this wood and sand it down and put these big metal things around. Hell, I don't know how to make a barrel. I'm not a cooper. But it was a lot of work. And sometimes they were a little bit small. Sometimes they were a little bit big. And if it was a little bit small, that meant although the brewery saved money on putting less beer in it, the bars and restaurants that bought that beer got screwed and got too little of it, right? And so that was bad. You'd lose clients that way. And if the barrels were way too big, then Guinness would be giving way more beer than they wanted to. And so Cunliffe was in charge of quality control as part of her Department of Statistics, and she went down to the area of the brewery where they had to evaluate the kegs, the barrels themselves, to determine whether or not they were the right size, right? So she said, okay, well, how do you do this process? Because we want to make sure we're doing every part of the brewing as perfectly as possible. They said, well, if we get a barrel, we weigh it, right? And if it weighs between this and this, we consider it to be a good barrel, right? And if it weighs below that or above that, then we say that it's sort of out of range and it's too small or too large. I said, okay, well, that seems to make sense. What do you do after that? Okay, well, if the barrel is out of range, so it's a bad barrel, we have to roll it up the hill back to the coopers so that they can essentially take it apart and fix the barrel. Okay, what happens if the barrel is in range, if it's a good barrel? Well, then we roll it down the hill, down to the brewery for filling and then loading onto trucks. And Stella said, wait a second. I think I know why we keep having difficulties with picking the right size barrels and getting the right size barrels. Why do we keep delivering them incorrectly if it seemingly is so accurate and based on this measurement of weight? Well, in this case, it was because the actions that the workers had to take weren't equal. If the barrel was out of size and bad, they had to push it up a hill. If it was in size and good, they rolled it down a hill. One was a lot of work, one was very little work. You probably start to notice over time that you have a little bit of a greater tendency to sort of fudge a little and take some barrels that might be close to the right size, right? And so you can see how quality control here was an issue at Guinness and how experimental control is an issue then as well. So when we design our experiments, it absolutely has to be the case that our conditions are equal in all respects whatsoever. And in fact, this is going to be really difficult, right? So in experimental design, we make sure we control the rooms that people are in, the type of paper that they're writing on, the pens, all sorts of things like that, whatever we find to be potentially relevant to their behavior, all because, as Stella Cunliffe once said, it's impossible to find human beings without biases, without prejudices, without the delightful idiosyncrasies which make them so fascinating, right? We're all weird, and we're all weirdly different from one another, which means if you put 30 of us in a group and say that's the caffeine group, that's still 30 weirdos that are really different from one another, right? And so we need to make sure that everything else that we can control is absolutely controlled, right, between those conditions. So I think that's a decent introduction both to Stella Cunliffe, but also to the idea of two sample studies. So far, we've been talking about single samples and known populations. Sometimes it's a single sample t-test because we know the mean of the population but not the standard deviation. Sometimes it's a z-test because we know the population standard deviation as well. But in either case, it was always a single sample. Now we want to talk about experiments that involve two samples, and that's why it's so important to talk about that level of control or equality between the samples. So how do we do that? How do you ensure that you have equal conditions, that you have the basically the same variables that have been controlled in one group are controlled in that other group, if it's two group of people? Well, one way potentially would be to recruit twins, right? They have the exact same genetic makeup, right? So get Lil and Phil, get them into your experiment, put one in one condition, one in the other. You know, at least genetically speaking, they are identical, right? We can't always do that, nor is it always the goal of what we want to do. So another thing we could do is matched pairs. In matched pairs, we identify a particular variable that we find to be relevant, say driving ability, alcohol tolerance, intelligence, even gender, right? And we find two individuals that match on that variable, and we place one in each of those two conditions, right? Ensuring that those variables then are matched between our two conditions. Other ways of doing two-group designs are independent samples designs. In an independent samples design, you grab from a larger population, right? You grab those randomly, true random selection, right? So that you ensure that whatever idiosyncratic weird differences there are in the population, you get those in the same proportion in your sample. And then from your larger sample, you randomly assign out what we called the randomized block design earlier on in the semester. You randomly assign these out to those conditions, right? A and B. Just keep knocking them over left and right until you've divvied up all your participants, and presumably then any of those weird idiosyncratic variables that existed in your sample will also be equally distributed across your two conditions. Now, one pro to this, of course, is that you could run, say, two groups at the exact same time, right? If you have an extra experimenter, so you can collect your data relatively quickly. A con could be that because you have two separate groups of individuals, in order to get the statistical power to achieve the central limit theorem that we talked about, we now need about 30 people in each of those two conditions, right? So 60 total people in your experiment. That in and of itself can be costly, both in terms of time, and if your experiment actually costs money, you're paying participants in some way, or you have to pay to rent equipment like fMRI, then it can be quite costly to have studies that involve lots of participants. Right? So that can be a con of that independent samples design. When that's the case, a opposing, I suppose, design, using a sort of within groups manipulation of the independent variable, is what we would call the paired or dependent samples design. And that's the design we're going to talk about here for the rest of this lecture. Oftentimes, this is as simplistic as studying individuals at time 1 and at time 2. So say you measure individuals on their ability to run the mile. So you get 25 people and you have them all run the mile and you measure how long it takes for them to run the mile. Then you give them some physical training and exercise regime for a 2-week period of time. You bring them all back. Now you measure them all again on how long it takes them to run the mile. Presumably that training exercise regime will have improved their running time on the mile, and you can compare their running times from time 1 to their running times from time 2, right? Pros here, you're using far fewer participants, right? You'd have 30 individuals studied 2 times instead of 60 individuals to fulfill your 2 conditions. A con could be, however, that you can't collect all your data at once, right? You have to wait until that second time point when you can measure them again. And there's a number of other pros and cons that I want to highlight as we sort of move our way through these next 2 videos to wrap up the paired and independent samples t-tests. Okay? So, starting with the paired samples t-test then. Let's talk about that design first and how we would analyze data from 2 groups where the groups are the same individuals measured 2 times. Okay, obviously in this case we have now 2 means instead of, 2 sample means instead of 1 sample mean and 1 population mean. Okay, that means we're going to be looking at a slightly different distribution than we've talked about before. So remember that when we looked at a sample mean, we said that this mean fits into a larger hypothetical distribution that represents all the possible values that sample mean could have been. So if I took the same size sample over and over and over again from the population, that's the average of those millions and millions of samples, that's infinite samples, would vary, right? According to a distribution. That distribution would be the distribution of means. Now, we're now going to talk about a group of individual and their average compared to the same group of individuals measured a second time and the average, right? In this case, we're going to be talking about mean differences because we're going to create what's called a difference score. Because I'm being measured 2 times, my scores are dependent, right? If I'm fast at time 1 compared to other people, then any training or exercise regime that happens that maybe boosts us all up should boost me up, and I should still be fast relative to that distribution of people that I'm in, right? And so what we can do then is link data for the same individual and create what's called a difference score, where I simply subtract the value of the measurement from the second time it's measured, or at the second time it's measured, from the first time it's measured. So Time 1 minus time 2, so to speak. I'll show you how to do this here in a second. That creates a series of different scores, the difference between your performance at time 1 and your performance at time 2. We can then create a mean of those differences, right? And that's the distribution we're going to talk about, right? The average of those different scores. What are all the possible values of the average of those differences? All right. So the distribution of mean differences. Okay. So you can see the Z formula up there. Sample mean minus population mean divided by standard error. You're going to see real quickly that the paired samples t-test looks very, very similar. Okay. So new equation. You tell me. We still have the sample mean. We still subtract off the population mean. We still have a measure of standard error in the bottom. And in fact, it's just the sample standard error that we've already begun talking about in the context of the single sample t-test. So realistically, moving from z-test to single sample t-test to paired samples t-test, it's about the easiest transition you could possibly expect, right? These formulas are almost identical. The logic behind them is identical. It's just that we're working with slightly different information in each case. With a z-test, we know population mean, population standard deviation. With a single sample t-test, we only know population mean, so we have to estimate variability using the sample. Right? In the paired samples t-tests, we have 2 samples. We don't know anything about the population. We're trying to say, based on what we know about these 2 samples, is it likely they come from the same population? Or is it likely that whatever differentiated them, right, that exercise regime potentially, did that now create 2 separate populations, a population of people who've never been trained and a population of people who have been trained, and these ones are now faster than these ones. Okay? So let's look at an example of this and see if it makes a little bit more sense as we walk through the numbers as well. We're going to do the 6 steps of hypothesis testing again, right? So we're going to keep doing this. As I told you, I know it's old hat. This is, been repeated now several times throughout the semester. It'll be repeated several more times before you finish this class. Here's our example. How long can you hold your breath in root beer? My kids love root beer. My daughter didn't used to, but my 2 boys absolutely love it, and now she's come right along and loves it as much as they do. So much so that one of them, the oldest, thinks it'd be cool to fill a swimming pool with root beer instead of water. Now, he and I debated the merits of such a move. Other than sugar in the eyes and everywhere else, I wondered whether you could hold your breath as long in root beer as in water. I suspect that with water you can hold your breath longer, but that being under root beer, the temptation to drink some of the frosty suds would be too great, and you'd not be able to hold your breath as long. So I had him recruit 5 of his friends, and we filled a swimming pool with root beer, and we timed them holding their breath, first under water, and then under root beer. So we had 2 swimming pools. All right, this is how long they could hold their breath, in seconds. All right, so for the 5 individuals, and him, right? So he was involved in here as well. So we got six total participants. Or no, I'm sorry. I have 5 participants. We must have recruited 4 of his friends, and then we included him too. So here's the times for how long they could hold their breath underwater. First person, 122, 131, 127, 123, 132. Okay, so those are our 5 participants. That first person, although they were 122 in water, they were 111. In root beer, right? And so there's a purpose for why those 2 are paired up right there. That is the same individual along that row. The next participant was 131 and 116, and then 127, 113, and so on and so forth. Okay, so I said one of the first things we do in a paired samples t-test is to create a difference score. A difference score merely subtracts y, in this case, the time for holding your breath under root beer, from x, the time holding your breath under water. Right, so we can do that really easy. X minus y. 122 minus 111 gives you 11. 131 minus 116 is 15. Right, and so on and so forth. Very, very easy. Now, moving forward with the rest of the problem, we're going to ignore the original data. We don't care about that anymore. We're just working with these difference scores. Okay? So pretend it's not there. Exit out if you need to. Now, we're going to run a single sample t-test using these difference scores. That's really all a paired samples t-test is. Okay, it's the same thing we just did. All we have to do first is create a difference score. Okay, so now that we have the different score, let's work through the process that we had to for the single sample t-test. We need a mean, right? We need to know our sample mean. We'll need to figure out the population mean, but I'll show you how to do that in a second. So sample mean, there's, let's see, 5 individuals. That adds up to negative 55, so negative for 11. It should be our, excuse me, not negative 55. That's the sum is 55. So divided by 5, then the average is 11. So that's easy. We've done averages a million times. Identify our populations. Okay, let's get started with our 6 steps of hypothesis testing. Population 1, people holding their breath underwater. Population 2, people holding their breath under root beer. Right? We're asking whether or not these would be different populations, meaning the amount of time they could hold their breath under water would be different from the amount of time they could hold their breath under beer, root beer. Distribution. What is our comparison distribution in this case? Now, we're not working with a sample average, right? An average of raw scores. We're working with an average of differences, right? All those difference scores. So the distribution is not a distribution of means, it's a distribution of mean differences. All the average difference scores, okay? Test and assumptions are all essentially identical, right? So you've got one group of participants that's been studied at 2 time points, so we know it's a paired samples t-test, right? That's the dead giveaway when it's the same people measured twice. The data are interval, right? It's times for how long they can hold their breath underwater. It wasn't random selection, it was just his buddies, but we're also not trying to generalize this much beyond. And the sample size of 5 is less than 30, so the distribution might not be totally normal, but again, I told you we're going to break those 2 assumptions for the purposes of classroom examples, but these would be things you would definitely want to look at for data outside of that context. Okay, so the next step then is to state the null and research hypotheses. The null hypothesis in this case would be that people can hold their breath for equal amounts of time, on average, underwater and under root beer. The research hypothesis then, the one that we're interested in, the one that we're hoping we can find evidence for, because this is why we did our research, is that people can hold their breath longer on average underwater than root beer. It's what we suspected based on our thinking, our observations, our background research, our love of root beer, right? So what's next? Determine the characteristics of the comparison distribution, that distribution of mean differences. What does that mean? Well, remember that basically just means find the other parts of the formula that you're going to need to calculate your t-test. What's the mean of that distribution of mean differences? What's the variability of that distribution of mean differences? So let's start with the mean. Whenever we look at our z or t formulas, we always take the sample minus the population mean. Why do we do that? Well, obviously we're trying to see how far apart it is, but what are we expecting to be the case if the null hypothesis is true? Well, if the null hypothesis is true, we're basically expecting the sample mean to equal the population mean, right? They won't be different, and you'd never have a statistically significant z-test or t-test, because they would always be the same, because the null says there are no differences. So if that's the case, then what would be the population average of a distribution of mean differences if the null were true? Right? So when z is 0, t is 0, we have 0 effect, right? The null is true. Well, what would be the center of that distribution? All the possible averages that you could take of different scores. If I took another sample of 5 people and I made them do the same thing and I created different scores and I created an average of that those different scores, and then I did it again and again and again and again and again until I created a distribution. Some of those different scores would be potentially in the positive direction, where people were able to hold their breath longer underwater than under root beer. Others would be in the other direction, where they could hold their breath longer under root beer than underwater, right? Null is true. You'd have an equal distribution of those things happening on both sides. And in fact, right in the middle, then, your average difference score would be 0, right? The null hypothesis would basically be saying that, on average, the most common thing that we would see is that whatever it took you in terms of holding your breath underwater, it's the same as what it's going to take you for holding your breath under root beer, because there are no differences here. And so that means the population mean of that distribution of mean differences, the center of that distribution of mean differences, is 0. I'll show you why that's important in a second. So let's return now to the sample, and let's get the other characteristics we need of our comparison distribution. We have our sample mean. We need to know our variability. That's the other part, right? So I told you we now have the center point. That population mean is 0. How far spread is the distribution? Well, we don't know from a population standpoint, so just like the single sample t-test, we have to figure it out based on sample variability. So here are our data. Told you we're not going to look at the raw scores anymore. We're using different scores, so we simply have to take the mean and subtract it off of each of those scores, just like we've done every other time we found standard deviation, right? So the score minus the mean, we'll do it again, right? Until we have all of these, get our sums of squares all the way up to 74, right? A nice whopping sums of squares. Then we can easily calculate our standard deviation. We know that formula. We introduced the n minus 1 in the denominator last time for degrees of freedom. We have 5 individuals, so that means the denominator is 4. So we put our sums of squares in the numerator, 74 divided by 4, square root of that, 4.3. Okay, so fairly easy. Again, we've done this several times. I'm just trying to show you how simple it is with the paired samples t-test and how similar it is to the single sample t-test. So remember that we work with standard error now because we are using sample variability, not population variability, and we are working with distributions of hypothetical distributions of averages, not with distributions of raw scores. So standard error is calculated by standard deviation divided by the square root of sample size. So 4.3 divided by square root of 5. And finally, we get the standard error of 1.92. So we're pretty much there. We're almost ready to solve it. We just need our critical values, and then we can calculate our t statistic and compare it. Okay. So critical values. I put the primary information that we've already calculated up above there, the population mean, variability of the sample, and average of the sample, as well as sample size and degrees of freedom. What do we need to calculate our critical values, our cutoff values? Well, we need to know our hypothesis. We need to know whether it's non-directional or directional. We need to know what the p-value is. If I don't tell you, then the p-value is 0.05. Okay, you have to determine the hypothesis, the directionality of the hypothesis, by looking at the prediction said in whatever the example is. So if we look back, it said people can hold their breath longer, on average, underwater than under root beer. So because it's saying that one breath holding time will be larger than the other time, right, a specific direction of a difference, then we call this a directional hypothesis. We can also see that it's a p equals 0.05 already stated here. Because it's directional, we know that means that the whole 5% error is in one tail. Because it's in one tail, we need to go to that spot in our t-table, right, where it says 0.05 and then in parentheses, one tail. Right, so you're following along. This is easy. Degrees of freedom are 4, so we go to that particular row, and we see that our critical value then is a t 2.132. Now notice that I put a plus sign, but I didn't put a plus minus sign. Why is it a t equals 2 plus 1.32? Because the way the t formula is set up, we are going to take a difference score and subtract off a population mean of 0. Okay, which means the value of that difference score is going to represent whether or not we predicted, or whether or not what happened was the x scores were higher or the y scores were higher, the time 1 or the time 2 were higher. So if holding your breath under underwater, which they did first, was longer as predicted, then those values would be higher because it's times than the times for under root beer, which came next, which means when we created our difference score, we'd always have higher values subtracting lower values, at least predicted, and we'd end up with positive directions, right? Positive difference scores, right? Because that's a positive difference score in terms of what we were predicting in our directional hypothesis, that's then going to predict a positive test statistic, a positive t-value. And so we want to put all 5% in the positive tail of that distribution. Had we predicted that times would be longer under root beer than underwater, and we still put it as water subtracting off root beer, then we'd be predicting a negative value for that test statistic, and we put all 5% over there, and we'd say that the cutoff is t equals negative 2.132. So I'll show you another example of that when we go through the independent samples t-test too, to try and really knock home this idea of the one-tail versus the two-tailed tests. So now all we have to do is calculate the test statistic, right? This is the easiest part. We simply have to take the t formula, the sample mean minus the population mean, and divide by the standard error, right? So we do that. 11 minus 0 divided by 1.92 gives you 5.729, and you round it to 5.73. So where does that lie on this larger distribution with our cutoff? Well, definitely into that shaded region, right? And considerably beyond our cutoff of 2.132. So how do we make that decision? Well, I guess statistically speaking, you'd say that 5.72 is greater than 2.132, so we reject the null hypothesis. But while we're statisticians, we are also humans and psychologists, so we don't speak that way. We would say people holding their breath underwater can hold it longer, on average, than under root beer. But then because we're also still psychologists and statisticians, we report the stats. So we say lowercase t, italicized, degrees of freedom equals your t statistic 5.72, comma, lowercase p italicized, less than 0.05. Less than 0.05, again, because we are rejecting the null hypothesis. We're saying the probability of this difference happening due to chance alone is less than 5%. Therefore, we can reject the null and say reasonably confidently that people can, in fact, hold their breath longer underwater than under root beer. Go figure. Okay, so given that it is less costly to do a paired samples design in terms of participants, right, and sometimes even time, if it takes a long time to run each individual participant, why wouldn't we always use that kind of a design? Well, here's a very, very contrived example, but an example that you simply couldn't study with a paired samples design. So my dad has this cool puzzle that he always called the Chinese lock. And I'm not sure where he got it. I'm sure my mom bought it for him. It looks a lot like this. I found a picture of this online, which apparently it's also called, I'm not even going to attempt that one, but it's also called the Devil's Needle, right? Or the Chinese rings puzzle. So it took him a while to figure out how to solve this thing. I don't honestly have any estimate of how long, a couple of days, maybe a couple of months. And when he finally solved it, I thought, oh, well, that was really neat. I want to see if I can solve it. So he put it back together for me, and he handed it to me, and I played with it for a couple of days. I was fairly young at the time, and I couldn't figure it out. Man, how the heck did he do this? And years later, I remembered this puzzle, and I went online. I'll show you a video actually here in a second, and sort of looked up how to do it, and realized that it's fairly complicated at first, but once you get the technique, it's actually really, really easy. It's just hard to sort of see what you have to do. So what if I had a research question that asked, does teaching someone a strategy decrease the amount of time it takes to solve the puzzle? So if I taught you how to do this, would you actually be faster at it after I taught you how to do it? Now, presumably you would, but we'd have to actually test that prediction. So we have two levels of our independent variable. We have one level where you're informed, right? You've been taught the strategy, and one level where you're naive. Can we do this as a dependent samples design? So let's talk about how you might do it. One option would be I study you first, measure how long it takes you to solve the puzzle when you have not learned the strategy, I've not taught you the technique, and then I teach you the technique, and you do it again. Possibly could work, but if you figured it out before, even if it took you much longer without a strategy, if your solution time is representative of you solving it, then probably by the end of that you figured out how to do it. And so me teaching you the strategy might not be what led to you being better. It might, in fact, just be that you had practice and you sort of figured it out. So in order to make sure that wasn't the case, we would have to do what's called counterbalancing and run the other design as well, the other direction. So then I would have to have a group of individuals that were taught the strategy, solve the puzzle, and then after they solved the puzzle under the strategy, I made them naive by somehow, I don't know, electronically erasing that memory of the strategy. It's not physically possible for it to go in this particular direction, and it's too confounded by practice to go in the other direction. Some designs cannot be paired samples designs. Okay, I know it's burning a hole in your pants. You really got to know how to solve this Chinese rings puzzle. So I'll show you somebody who's trying to beat the record. He screws up a couple of times, but he does pretty well. All right, here it is. Okay, that's it. We're done. We got one more video on independent samples t-tests, and then we are set and ready for an exam. I know you're as excited as I am. All right, cheers.